that moves parallel with the movement of the wave, with the movement of the particles, and that is longitudinal waves. If you're kind of getting lost in all these words, don't worry, I'm going to break it down and I'm going to point out what it is that I'm talking about on this slide, and we're going to work our way through it. So looking at the top, waves are divided into two types: mechanical, which needs a medium, a solid, liquid, or gas. If it doesn't have a solid, liquid, or gas, then mechanical waves are not going to make it anywhere. The energy cannot leave an area and go from point A to point B. Electromagnetic waves, because of their electric and their magnetic field, can travel through empty space and through other materials as well. So it has the energy levels to move through nothing, outer space, or it can travel through other materials as well. Let's jump over to the mechanical side. With those waves that need to have a solid, liquid, or gas, longitudinal waves, oh, look at it, I forgot a T right there. I'm going to have to go in and fix that. You'll see that when you start your own presentation. Mechanical waves can be transverse or longitudinal. Actually, you know what I'm going to do? I'm going to ask you guys to go and draw a little T in there for transverse for me. So add transverse. Longitudinal waves are the other kind. And to step back, I introduced to you transverse waves of saying that the waves are going to move up and down while the energy moves left and right. And those directions were perpendicular, and they created a right angle. In longitudinal waves, everything moves along with the wave and the energy. So do the particles. You're going to see in just a moment. So let's fill in the blanks here. They need a medium. You're going to be writing the word medium. And down here, EM waves are only transverse waves for that one. Okay, so we're going to get into reading here, and I'm going to read aloud, and when I'm reading aloud, you need to go through Pear Deck and do the following. Highlight the following words as you read them. We're looking for words like compression and rarefaction. We're looking for words like parallel. That's in the definition. I know that it didn't show up anywhere else as we're looking. And then vibration or vibrate, because that's what sound waves are all about. Let's get started. Longitudinal waves. In a longitudinal wave, the particles of a medium vibrate back and forth along the path that the wave moves. You can make a longitudinal wave on a spring. When you push on the end of a spring, the coils of the spring crowd together. A part of the longitudinal wave where particles are crowded together is called a compression. When you pull back on the end of a spring, the coils are pulled apart. A part where the particles are spread apart is a rarefaction. Compressions and rarefactions are like the crests and troughs of a transverse wave, as shown in Figure 6. We'll take a look at that in just a moment. The sound waves. A sound wave is an example of a longitudinal wave. Sound waves travel by compressions and rarefactions of air particles. Figure 7 shows how a vibrating drum forms compressions and rarefactions in the air around it. The question that matches on the right-hand side, what kind of wave is a sound wave? So go back and take a look if you're wondering what that is. In my little video right here, I'm going to show you a slinky. So we had talked about transverse waves as going up and down with that energy. And so what I can do is I can make the up and down motion where we know that the energy is traveling from here to here. The particles and the medium are going up and down. But when I am making a longitudinal wave, what I'm going to do is I'm going to group these springs right here, these coils together, and when I let them go, instead of moving up and down, they're going to move to the other side of the screen. Okay, now notice that the springs are moving here, this way, back and forth. Now that's parallel to the waves that are happening. And I want to talk about why this is the case. So in the picture for figure 7, I remember looking at this figure for the first time, and it said that this is a drum, and I was trying to see that, and actually they are putting a drum up sideways. So here we have this drum. I borrowed this from my husband, and he said, be careful, that's a 1960s something or other Ludwig. It's been played for years. So I promised him I'd be careful with it. But as I'm talking into it, I'm already hearing an echo going on. But see, this drum works somewhat like a trampoline for air particles. If anything hits this drum, it's going to cause I don't know what to call it, the surface of the drum to hit and bounce back, okay? And so when it bounces back, it pushes these waves into groups. And when those groups called compressions reach your eardrum, they're going to be tapping on your eardrum the exact same way that my sound waves are tapping on this drum. It's just smaller in size. So instead of a wave going like this, the wave is going like this, further out in those groups. The only way that you can hear my voice is because the speaker in your Chromebook or the speaker in your headphones that you're listening to are actually creating compressions that are going against your eardrum. And it's so interesting how our brain can hear just the tiniest differences. You know the difference between the compressions that hit from my vocal cords. You can tell the difference between mine and Mrs. Wire's based on how we sound and how our vocal cords work. But basically, a drum is like a trampoline that's creating those groups of particles that we have. All right, so hopefully that helps you in understanding how compressions are getting squished together. So I can show you this in a slinky, in grouping them together and saying, okay, if I grab this group and it travels across my screen, that's what you're seeing in the picture for figure 6. So as you look, see where these little loops are grouped together? That's a compression. This is a compression. This is a compression. And that's a longitudinal wave that's traveling through a slinky, which is different from a sound wave. A sound wave does not have metal coils in order to transfer it. Instead, we have all of these particles in this space that when they move, they're going to be pushing against each other and creating those compressions of air. So I'm challenging you to draw the pattern of particles as longitudinal wave sound moves from point A to point B. Basically, I forgot to create, I wonder if I can draw here. I forgot to create this on Pear Deck, so I'm going to have to go in officially, and I'll change that T in transverse now. But I'm going to create these particles so that you can create the same thing and know what to do. So if this air horn is sending sound to the eardrum, we're hoping it's far enough away that it's not causing terrible damage. But if we have this, we know that immediately it is going to be sending these particles are all going to get hit and they're going to push into the next space. Now, if these particles are getting pushed, grouped together, then that means that there's not very many to fill in the spaces between in those rarefactions. The reason that they call them rarefactions, if you notice the coincidence, rare means not very many. So I'm creating, and I'm spending a lot of time doing this. So there's another compression. And if it's the same value of sound, your compressions and rarefactions will look the same throughout the entire space. So for those of you who are, just looking for, hey, Mrs. Smith, tell me quickly what I should do. If you get it, if you know that I'm spacing these grouped together particles about an inch apart on the screen, then you should keep on repeating the compression and rarefactions. Can you guys kind of see the pattern that I have here? I feel like I'm playing a video game. Okay, so I'm going to continue this across the page. So right here, I'm going to draw, this is a compression. I'm going to put a C. Whereas this space right here, there aren't very many of them in that area. That's a rarefaction. And if you follow a pattern, it goes compression, whoop, rarefaction. Compression, rarefaction, compression, rarefaction. You should do this all the way across from the horn to the ear so that you're showing that you see what air particles are doing. When we were talking about transverse waves, we were talking about, okay, if there's a crowd in a stadium and you're creating a transverse wave, everybody is standing up and sitting down. And I had asked if that was an actual version of a wave, and I got a lot of great answers. The true answer is that it's shape. The people are acting in the shape of a wave, but this person right here is not actually giving any energy to the next person down the row. So it's not actually behaving like a wave. No one is being forced to pass energy. Anybody who just wants to enjoy their hot dog can stay in their seat and not have to pass energy at all. So now let's talk about a longitudinal wave. Let's say a lot of people are standing in line. It's a crowded area. And let's say someone becomes frustrated and someone else loses their balance. If they fall at the beginning or the end of a line and that pushes on someone, that can actually cause like dominoes to push against people. And instead of going up or down, we're seeing this compressional group. And as after, you fall and you pull yourself back up, and you've become part of that longitudinal wave. If you were to behave like a wave, it would kind of look like that. If that's a helpful way to imagine how air particles are behaving, as they get pushed forward, but then they return to where they are until the next compression comes in and pushes them forward again. And the value of volume and high pitch and low pitch all depends on the style of energy that comes through the air. And we'll learn more about that next week. So this week is about longitudinal waves. And next week is all about those different properties. Okay, moving on. I'm done using this. I get back to my pointer, but I want to change slides here. Oh, thanks for being patient with me. Okay. Flashcards to make for today. You need to make a flashcard for longitudinal wave, make one for compression, for rarefaction, not to be confused with the word that's very similar to that as refraction. So we are going to have actually rarefaction, refraction, and reflection, which is fun if we can say it really fast 5 times. That's all that I have for tonight. Longitudinal waves are all sound waves. I guess I do have one more question. When we're watching Star Wars movies, that's one of the goals for my family. We're watching the whole series. My kids have never seen it, so we're working our way slowly through each of those. When an explosion happens in outer space, can you hear it? Is a sound made in those explosions? And so I'm thinking about all those Star Wars movies where there's the battles that are going on in outer space. Is if there's all these explosions and you can see it, but can you hear it? All right. Have a wonderful day, you guys. Finish this Pear Deck. You're going to learn more tomorrow in Ed Puzzle, and we're going to keep on going with how longitudinal waves behave. Talk to you later. Bye.